Okay, well, thank you very much. Welcome to Module 2 of our Advanced Dran-View training, where we're going to speak about the Harmonics and timeplot calculator. So what the Harmonics and timeplot calculator does is somewhat related to the math channels. And some of the things that I spoke about in the math channel section, as far as being aware of the different recording techniques in your instrument, following standards such as 61000-4-30, and there's two kind of important things to recognize with that again, is that it does the one cycle calculations per 61000-4-30, but half cycle stepping means that you're looking at one cycle, but when you do your RMS calculations of a wave shape, but you're only advancing your one cycle window by a half a cycle. And then you do it again and again, and you have these overlapping half cycles in your computations. It's the way 61000-4-30 Class A defines how to work. In addition to that, there's 200 millisecond windows for harmonics and other things, where at 60 hertz, you're looking at 12 cycles, and at 50 hertz, you're looking at 10 cycles of 200 millisecond data, and that's where your harmonics come from. So just recognize these things. That Dran-View is, for the most part, looking at one cycle at a time, but you also have the ability to vary the width of the window within what's calculated within Dran-View. So like as an example, if I want to do either math or I want to do the harmonic and time plots tool, if you remember from our basic training that we had on March 3rd, we have this time frame tool. And I didn't really elaborate on one of the capabilities of that, is that you can take any part in time and highlight it, and that will be the time period that Dran-View defaults to use for whatever function or calculations that you just asked it to do. So as an example, I have my event details as a pane here. So let's say this is completely hypothetical. I'm going to go time range. And let's just say, for the sake of argument, I'm interested in doing my harmonic time plot calculations on that period of time. It's going to give you an example of how many samples are included in that. But when I go compute something, or I do this on the math channels, I believe, it'll only work on this small subset of your data, not the entire however many cycles are in here. Maybe 5, 7 cycles are in there. So you have the ability of marking the period of time. So the window in Dran-View is more variable in nature, starting at a cycle. The windowing in the instruments are standards based. So just remember that these are slight differences in precision. In the end, you will get very similar results of different window sizes when you apply data within that time frame. So that's just a note. So I'm going to turn this off. Now let's talk about the harmonic and time plot calculator. Again, very similar to the math channels. What it's doing 1, 2, or 3 things. And what I mean is, it's either computing new data that is not available in the instrument, which is its primary function. A good example in this application is the frequency. So, and I'll show you that in a little while. So this is a generator test. And in a generator test, it's very important to follow the frequency, the cycle by cycle frequency. So we're going to focus on this application because it's an excellent demonstration of the time plot and harmonics calculator. So it's computing new information for you. It also has the ability, similar to the math package, to recompute data from the instrument if you wish to do that. So it has the ability to do that. And the third one is actually mixing them together. So you can actually show what came from the instrument, and you can also highlight what you've recomputed, and either additionally or just mirrored the computation if that's something that you want to do within the capabilities of the harmonic and time plot calculator. So when we do this, like the math channel, these are going to show up as selectable channels. So how do we do this? So I'm going to start with the time plot. I'm going to go here and I'm going to make the time plot my active pane. Again, it's got that blue band around it, or bar around it. I'm going to go to data, and you can see here the harmonic and time plot calculator. So I'm going to select this. It's going to pop up a window. Now, most of your guys, it's going to default to being off. You may even see it show up like this, depending upon, I really don't remember how Dran-View installs, but it'll probably default to off in this mini window. You go more, and now you have all the parameters available to you and all the things to go through with the harmonic and time plot calculator. We'll cover this in general, but I'm going to give you an example of its capabilities first before we continue. So you can go through and you can have this go through the default parameters. These are the things that are automatically enabled by Dran-View based upon its default configurations. or you can go to the custom and you can make your own custom things. So you have the ability to turn on or turn off any particular parameter, and this will be now computed within Dran-View. Also, you have the ability to make this your new default setting. So when you open and close sites in the future, this is going to automatically come on for you by default. So let's focus on that frequency application. Again, this is a generator step load test. So it's extremely important to the customer here and the end user to show the response of the generator based upon these step loads that are introduced. So one of them is the cycle by cycle frequency. When you get frequency from the instrument, that is a 200 millisecond average that's recorded. And that's defined in the standard. So that is not cycle by cycle information. However, you have the AC cycles, as you can see over here on the right. So Dran-View, using the Harmonic and timeplot calculator, has the ability to compute cycle by cycle frequency. So how do we do it? So the first thing I'm going to do is I'm going to shut off all the other things just by unchecking them. And you can see I left frequency there. So I continue to make sure everything else is unselected. You can see I added frequency here. So it's going to recompute frequency for us. All right. So I'm going to click OK. And you're going to see Dran-View is going to start to crunch. You can see that pop-up window. Now it's going to start to crunch. So what it did is it computed the frequency based upon these wave shapes on every waveform within the Dran-View database that came from the instrument. Now you have the availability to turn that on just like any other channel. So we're going to give a real life example here. So you can see it defaulted to the math channels that we're looking at before, but I'm going to go right here to the primary measurements that came from the instruments database. Now, when you have Dran-View, basically its default frequency is right here. It's total frequency that comes from the instruments. And again, that's a 200 millisecond average. So that's good in 90% of the power applications. However, it's not really applicable for the cycle by cycle frequencies that we're talking about here. So you can see I have also these other individual A, B, B, C, and CA frequencies that have been computed by the wave shape data, this information recorded in your database. So I'm going to just select AB as an example. I'm going to take, here's our voltage RMS for phase AB and our current RMS for phase AB. So we're going to look at that within Dran-View right now. So here you can see, here's the voltage phase AB, the step load changes on the AB phase, and this is the cycle by cycle frequency for that. And overlaid on top of that is the total frequency from the instrument. You can see right over here. So to demonstrate the differences, I'm going to right click, go to properties. Now I'm going to just keep frequency here. So you can see the power of this plot, where I have, here's the influence on the power system, these step loads, and here are the changes in frequency on a cycle by cycle basis as the step loads increase in each pulse. And you can see the impact on the frequency. We're going to show that here in the time plot, but in the next step or 2 steps ahead, we're going to show that on the event details as well. So my point being before is to show you the difference in the frequency recorded by the instrument under frequency here, which is the total frequency, versus the cycle by cycle. So I took away the voltage and the current, and here is our computed frequency here by Dran-View in the Harmonic timeplot calculator. You can see below, this is the frequency that came from the instrument, the average frequency in the database. All right. And you will see in general, they follow each other, but look at the precision that you have here in what's computed by Dran-View, because it's based upon these individual cycles. So again, as we're looking at here in the timeline, this is the entire recording duration from the beginning of the test all the way through to the end of the test. So you can see why the power of the cycle by cycle frequency is important. And you're looking at the step load impulse changes from that. Where a lot of the power comes from are in the event details, where you can look and you can see here all our event markers of what's been recorded. And here's all the different step load changes. Here's the first step, and you can go down and find the next step. And you can see we're moving our event marker to all these different things. I can highlight them on the left, or I can go select them on the timeline tool here. Well, the important thing here is for many of these applications, and if I'm the owner, I'm the guy commissioning the system or gal commissioning the system, well, what was the cycle by cycle frequency? How did that change when I, stepped up or stepped down this current? So just like we computed it for the timeline, we can do the same thing here for the event details. So just as anything, I right click, I go to properties. Okay. Now I'm going to turn off our wave shapes. So actually, I'm going to just keep our voltage wave shape. Actually, I'm going to start with the current wave shape. So this is going to show me the current waveforms recorded on the A phase. I'm going to go to basic metering. I'm going to shut off the voltage here, and I'm going to just go for the frequency of AB. This is what we just computed in the Harmonic time plot tool. I'm going to click OK. Now you can see the frequency response, 60 hertz, and you can see how the frequency rose when this is a turning off. You can see the current going down. So as I go through and I look at all these different events, like I'll select over here as an example, you could see, I'll go select the actual beginning of the event. You could see here a step load change all the way up. We're over here. This likes about 75% of the load of the system. You can see the difference in the frequency here. Here's the amperage and the cycle by cycle current recorded, and here's how the frequency drifted down as that load went up and that load stabilized over here. So you can see the direct result of the impulse. Again, we're showing frequency. So let me go back to the current here. Say go voltage and current. We'll add that, and this will make a little bit more sense over here. So here are step load changes. We're marking this point, and this was actually to 50% of nominal. Or no, I'm sorry, that was 75% of nominal. So now you can look at any one particular point in time in any event, and then go look at the response of the frequency in this application. Extremely, extremely powerful for this particular generator application. So knowing what we learned before, let's go look at the details of the harmonic and time plot calculator. Again, it defaults to off when you install Dran-View. However, when you come back, it'll be in the last state that you left it in. So you have the individual capability to include or exclude any one of these basic parameters, harmonics, symmetrical components, and you have the ability to tune, which we'll get to in a second, what Dran-View is going to do with this information and the level of precision. So you have RMS, peak, THD, frequency, power, phase information, totals. So these are things that could be computed or recomputed to the point in one of the chats we had before, if it's already in the instrument database. We're not saying that you need to recompute information, but there are applications where that may become beneficial to you. So one may be computing THD from wave shapes that have been recorded. All right, maybe you just want to do cycle by cycle THD. Again, THD for the instrument is going to be on a 200 millisecond window average. So these are different applications. Only you folks would know how to best apply this for your particular application. We can certainly make suggestions for you, but this is just in general how this works. So you go through the basic capabilities. Again, you have the default, which will turn them on for you. The custom, you completely control what these are. And again, these become selectable channels that are mixed in with the parameters from your instrument. So as an example, when I go down to the output options, you have the ability to control how much information you're including. The one thing that's important to realize is that some of this that you tell it to do can take a long time to compute. If you tell it, like as an example, where you want, number of data points, it defaults to 2 samples per cycle, just so it's small. You could use all the samples in the cycle, or you can select anything to kind of downsample your computations. And what I mean, just as a hypothetical thing, it'll take twice as long to calculate something at 128 data points per cycle, samples per cycle, versus 64, or 256 versus 128. You're asking Dran-View to do twice the work. You may see a burden in that, in the amount of time it takes for Dran-View to process it, and also depending upon the speed and memory of your computer. So these are things that you have individual control over. So you can do the number of samples per cycle that's included. You can say, and for harmonics, the number of harmonics to calculate. So you can, I want to go out to the nth harmonic. You could say how many harmonics to include in the THD. This is actually important because some different standards around the globe require different numbers. 50 is a very round number for IEC 61000-4-7, which are meters, certainly, or instruments supports part of that class I was talking about. And also that's important for IEEE 519-2014. However, newer standards such as the new G55 in the UK, well, that requires up to the 100th harmonic be included in THD. So these are some of the things that you can add value to the data, do things that the instruments don't do natively. So that's another application for this. Now, a very important thing here is if the parameter has been measured by the instrument, what do you do? Okay. You keep the original parameter. So like for the RMS example, okay, I'm not going to do anything. The instrument has it. I'm not going to recompute RMS. Or mix. Mix means I have both. In the case of frequency, as we had before, frequency came from the instrument, but it came with that 200 millisecond averaging based upon the standards, but I wanted cycle by cycle. So I'm going to mix them. So I have the ability to choose either one or both of them individually, which is exactly what we've done here. Again, this is the computed from the harmonic time plot calculator, and this came from the instrument. Or I can say overwrite. So Dran-View is going to replace the new computations or overwrite the ones that came from the instrument with those that were just computed here or more appropriately recomputed. So this is your choice as well. And there's more advanced capabilities here. Well, actually, right over here, this is what to do by default, okay? So automatically generate default parameters when a file opens of this type is opened, okay? So I don't want to do that at all. I want to do it if the file only contains waveforms or always. So keep in mind, this may apply differently depending upon the type of instrument that the data has come from, as well as the type of data that is in the database that's based upon your survey settings and your recording settings, okay? So some other more advanced parameters, the channel may run on different frequencies. This is important to our application. So if I were to do this again, I'd select this. So that means that phase A, phase B, phase C, or channel ABC on the instrument, you're saying that the frequencies may not be locked. In a generator, a standby generator, or an islanded system, that may be important to you. In a utility system, you know, A, B, and C are locked at the generator stage, and you're not going to see drift in normal operation. However, in standby generators, which is this example, you could very well see a different frequency on A, B, and C. And this is going to tell you that to compute the individual ones for you. All right. And other things, you know, displaying only one average data point per waveform. This is ways to optimize what Dran-View will do. I won't go into a lot of that. However, this one over here, increased harmonic accuracy, I believe that has to do with the precision of the variables that's recorded. So in summary, what you'll find is very powerful capabilities to compute information from data that's been recorded by the instrument, both journal points, but also wave shapes to add value and create information that the instrument was not capable of recording, like this cycle by cycle frequency, or maybe recompute information that you neglected to turn on at the instrument level. So extremely powerful for this application.